Example 1. Write down the first 5 terms of the sequence given by Tn equals 6n minus 4. Hence, express the sequence using a recurrence relation. Now this subscript n represents the position of the term. So when n equals 1, that represents the first term. N equals 2, that represents the second term. N equals 3, T3, that represents the third term, and so on. So to get the value of the first term in the sequence, we substitute n equals 1 into the formula and then evaluate it. So T1 is equal to 6 times 1 minus 4. T1 equals 2. So that's the first term of this sequence. T2, that's the second term in the sequence, is 6 times 2 minus 4. Therefore, T2 equals 8. T3, third term in the sequence, 6 times 3 minus 4. Therefore, T3 equals 14. And following the same pattern, of course, T4 is equal to 20, T5 is equal to 26, and so on. So we can see from this pattern, 2, 8, 14, 20, 26, that we can get to the next term along just by adding 6 to the current term or to the previous term. So expressing this as a recurrence relation. So that means coming up with a formula of sorts that expresses the current term in terms of the previous term or terms. So Tn, so whichever term we deem the current term, for example, let's say 14, we can get to 14 by taking the previous term and then adding 6 to it. And likewise, to get to 8, we can look at the term before, the 2, we add 6 to that, and we can get to the current term. So we can come up with a general rule called a recurrence relation. Tn, the current term, is equal to the previous term plus 6, where T1 is equal to 2. So you sort of have to have a starting point so that the sequence has to start somewhere. So we can define our starting point here, T1, so in other words, n equals 1 to 2, and then every other term sort of after that, we just take whatever the current term is or the previous term, and we just add 6 to it. Example 2. Find a non-recursive formula for Tn given the recurrence relation Tn equals Tn minus 1 plus 10, where T1 is equal to 14. So the strategy here is to write out a few terms, usually 4 or 5, to see the pattern. So T1 is equal to 14, so that represents our first term, and we get the subsequent terms by adding 10 to the previous term. So adding 10 to 14, we get 24, adding 10 to 24, we get 34, 44, and so on. So from this pattern, we can see clearly that Tn is equal to 10 times n plus 4. So for example, n equals 1, 10 times 1 is 10, but of course we need to add 4 to compensate for the difference. So we get 14, test it again with another term, say the second term. 10 times 2 is 20, plus 4 gives us 24, maybe one more for good measure. 10 times 3 is 30, 30 plus 4 is 34, and that gives us our third term. Example 3. Determine whether 300 or 400 are terms of the sequence Tn equals 7n plus 20. Now the strategy here is that we substitute 300 and 400 for Tn, and we're going to test each one of those separately. Solve for n, and if we find that n is a positive integer, that refers to the particular term in the sequence. Therefore, that term will be a term in that sequence, and n represents the position in that sequence. But if we get a value of n anything other than an integer, then that term is not in the sequence. So let's test Tn equals 300. So we're going to form the equation. 7n plus 20 is equal to 300. So we're just going to let Tn equals 300. Rearrange the formula and solve for n. So 7n equals 280. And dividing both sides by 7, we get n equals 40. Now, since n is an integer, in fact a positive integer at that, T40 equals 300. N equals 40, so that means that 300 represents the 40th term in this sequence. Now let's test Tn equals 400. I'm going to test it the same way. Form the equation, 7n plus 20 equals 400. Solve for n, so dividing both sides by 7, we get n equals 54 and 2/7. And that doesn't make sense as a position number. When you're talking about a position or a rank, you know, the first, second, third, fourth, it doesn't make sense to have a rank that's fractional, in fact. Now, since n is not an integer, Tn equals 400 is not a term in the sequence. Example 4. How many negative terms are there in the sequence Tn equals 12n minus 100? The strategy here is to solve this as an inequality by setting Tn less than 0. So we're interested in the values of n that represent the particular terms or the position of the terms that we're interested in, such that 12n minus 100 is less than 0. So let's set up the inequality. 12n minus 100 is less than 0. Solving for n, so 12n is less than positive 100. Dividing both sides by 12, we have n is less than 100 over 12, and 100 over 12 is just 8 1/3. So the first integer less than 8 1/3 is 8. Hence, the negative terms are from n equals 1 to n equals 8. So in other words, t1, t2, t3, all the way to the 8th term. So therefore, there are 8 negative terms in the sequence. And you can test this, of course, by substituting in, for example, n equals 1. Of course, you're going to get a negative number. Check n equals 8, since that's the highest value of n, such that 12n minus 100 is negative. 12 times 8 is 96. 96 minus 100 is negative 4. So the next term then beyond that, so n equals 9, of course, that will result in a positive value there. Example 5. Find the first positive term of the sequence Tn equals 7n minus 60. The strategy here is to solve the inequality by letting Tn greater than 0, and then finding an integer value of n such that 7 times that value of n minus 60 will give you the smallest possible positive Tn. So let's set up the inequality. 7n minus 60 is greater than 0. Adding 60 to both sides, we have 7n greater than 60. Dividing both sides by 7, we have n is greater than 60 over 7, or 8 4/7. So Tn is positive for integer values of n such that n is greater than 8 4/7. So the next integer value of n greater than 8 4/7, of course, is n equals 9. And we can test that by substituting n equals 9 into the original formula. So T9, the 9th term, is equal to 7 times 9 minus 60. 7 times 9 is 63. 63 minus 60 is 3. So T9 equals 3. So therefore, the first positive term in the sequence is the 9th term, 3. Example 1. Test whether the following sequences are arithmetic progressions, APs. Part A, 5, 9, 13, 17, and so on. Now a sequence is arithmetic if Tn plus 1 minus Tn is equal to Tn minus Tn minus 1. So if we choose any 3 consecutive terms of the sequence, let's say, for example, in this case, we chose 17. We did 17 minus 13, and then compared that with 13 minus 9. So the difference between these two terms and the difference between these two terms should be identical, common difference. 17 minus 13 equals 4, and 13 minus 9 also equals 4. So therefore, the sequence is arithmetic. Let's have a look at part B. 2, 3, 5, 8, and so on. Again, just choose any 3 consecutive terms. So I've chosen 2, 3, and 5, and compared the difference between those 3 terms. So comparing 3 and 5, 5 minus 3 is 2. And comparing 3 and 2, 3 minus 2 is equal to 1. Obviously, it's not a common difference, since the difference between 2 and 3 is not the same as the difference between 3 and 5. Therefore, the sequence is not arithmetic. Now, just as a side note, if we go back to what was written here in red, and we made Tn the subject of the formula, then what you end up with is the average of 2 terms. So let's say we chose a term and we looked at the terms on either side of it, so Tn plus 1 and Tn minus 1, and we took the average of those, it should equal the term in between. So in this case, let's say, for example, the average of 5 and 13, so 5 plus 13 is 18, divided by 2 equals 9, and that equals the term in between. So basically, it's just a rearrangement of this definition here, but it is another useful way to show if a sequence is arithmetic or not. Let's have a look at another interesting example. So part C, we have this sequence, ln of 2, ln of 4, ln of 8, ln of 16, and so on. Now, just initially, it doesn't look like it's an arithmetic progression. In other words, just due to the nature of the numbers themselves, 2, 4, 8, 16, they themselves are not arithmetic, since the difference between them, it's not common, it's not the same. However, using one of our logarithm laws, in fact, we use the law number 3, where we express the number inside the logarithm here as a power. So 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 cubed, and 16 is 2 to the power of 4, of course, and so on. And applying the log law number 3, where we take the index and bring it out to the front, this sequence can be rewritten as ln of 2, 2 ln of 2, 3 ln of 2, 4 ln of 2, and so on. Now again, choosing any 3 consecutive terms. So for example, 4 ln 2 minus 3 ln 2, and just working out the difference, and that's just ln of 2. And then comparing it with the difference of 3 ln of 2 minus 2 ln of 2. And of course, that's also equal to ln of 2, so there's a common difference there. So therefore, the sequence is arithmetic. Example 2. Find the first negative term of the AP with A equals 151 and D equals -3. Firstly, let's write out the first few terms of the AP, just so we can see a pattern. Now, A represents the first term and D represents the common difference. So that's the difference between any 2 consecutive terms. So starting off with 151, subtract 3, one lot of common difference there. 151 minus 3 is 148. 148 minus 3 is 145, 145 minus 3 is 142, and so on. Next, let's determine a formula for the nth term Tn. Starting with the general formula here, Tn equals A plus n minus 1d. So Tn equals the first term, which is 151, plus n minus 1 multiplied by the common difference of -3. So substituting in those 2 values into the general formula here, we have Tn equals 151 plus n minus 1 multiplied by -3. So let's expand the brackets and simplify the algebra. We have Tn equals 151 minus 3n plus 3. That's -1 multiplied by -3. Gives us the +3 there. And collecting like terms, we have Tn equals 154 minus 3n. Lastly, let's solve for n by letting Tn less than 0, or setting Tn as Tn less than 0. After all, the question does ask for finding the first negative term of the AP. Hence why we set Tn less than 0 there. So let's form the inequality. Okay, so we'll take our general formula here for this particular AP, so the term for, to find the nth term, that is, 154 minus 3n less than 0. Subtracting 154 from both sides, so we'll make -3n the subject of the formula, so -3n is less than -154. Next, we divide both sides by -3, and in doing so, we need to flip the inequality sign. So instead of it being less than, it now becomes greater than. So n is greater than 154 over 3, and just expressing that as a mixed numeral, n is greater than 51 and a third. So we need the next integer, or an integer that is higher than 51 and a third, of course. So the next integer along is n equals 52, which means that's the 52nd term. That is the first negative term of this AP. So T of 52 is equal to 154 minus 3 times 52. So going back to our formula for the nth term of this particular AP. And we have the 52nd term, T52, is equal to -2. Example 3. How many terms are there in the arithmetic progression 15, 26, 37, ... 6,395? Now, firstly, we don't need to prove that this is an arithmetic progression. We're told so in the question, so we can find the common difference just by taking any 2 consecutive terms. So just be mindful that there may be questions where you may need to prove that this is an arithmetic progression first by comparing any 3 consecutive terms and comparing the common differences. But in this case, we're told it's an AP, just take any 2 consecutive terms, subtract one from the other to find the common difference. So in this case, determining the formula for Tn, or the nth term of this AP, we have a equals 15, our first term, and the common difference is found by taking any term and then subtracting the term before it. So for example, 37 minus 26 gives us 11. Substituting in these two values into the general formula for the nth term of an AP. So Tn equals 15 plus n minus 1 multiplied by 11. So that's from a plus n minus 1 multiplied by d. Expanding the brackets, we have Tn equals 15 plus 11n minus 11. And combining the like terms, so 15 minus 11 of course is 4. We have Tn equals 11n plus 4. Now 6,395 represents the last term, so we'd like to find the value of n that corresponds to this particular term here. So we're going to solve for n, given that Tn, our last term, is 6,395. So let's solve for n here, given 11n plus 4 equals 6,395. And of course we're going to make n the subject of the formula. So subtracting 4 from both sides, we have 11n equals 6,391. Next we're going to divide both sides by 11 to make n the subject of the formula. So n equals 6,391 divided by 11, and we have n equals 581. So interpreting this result, what this means is that this particular AP has 581 terms. Example 4. Write out the first 5 terms of an AP, given the 10th term, T10 equals 52, and the 17th term, T17 equals 31. Now the strategy here is to form two equations involving the nth term of an AP, and applying the fact that T10 equals 52 and T17 equals 31, so one for each equation, and then solve those equations simultaneously to find the first term A and the common difference D. Then we can write out the first 5 terms of this particular AP. So for equation 1, I'm using the fact that T10, or the 10th term, equals 52, so that means n equals 10. So 52 is equal to A plus 10 minus 1 times D. And the second equation uses the fact that T17 equals 31, so the 17th term, n equals 17 of course. 31 equals A plus 17 minus 1 D. Then we're going to solve simultaneously by elimination. So equation 1 minus equation 2. So 52 minus 31 is 21. A minus A is 0, so those two are eliminated there. And then we have 9D minus 16D. So we have 21 equals negative 7D. Dividing both sides by negative 7, we have D equals negative 3. So that's the common difference. So next, to find A, so we can use either one of these two equations. Substitute D equals negative 3 in either one. So I've just used equation 1 just for convenience. 52 equals A plus 9 times negative 3. And 52 equals A minus 27. Adding 27 to both sides, we have A equals 79. So now we can form an equation for the nth term of this particular AP. So Tn equals 79 plus n minus 1 times negative 3. Expanding the brackets and collecting like terms, we have Tn equals 82 minus 3n. Now we can write the first 5 terms of this particular AP. So the first 5 terms of the AP are 79, 76, 73, 70, and 67. Example 1. Test whether the following sequences are geometric progressions, GPs. Now a sequence is a GP if Tn plus 1 over Tn is equal to Tn over Tn minus 1, where Tn minus 1, Tn, and Tn plus 1 are 3 consecutive terms of the sequence. Now another way to test if a sequence is a GP is if we take, say, 3 consecutive terms and we square the middle term and we multiply the 2 terms on either side of the middle term and we find that they are equal, then that's also a geometric progression. So let's have a look at part A. We have this sequence here, 5, 15, 45, 135, and so on. Now, by observation, we can see that if we take the first term, multiply it by 3, we get 15. We take 15, multiply it by 3, we get 45. 45 multiplied by 3, we get 135, and so on. But just applying the test, so if we choose, for example, 3 consecutive terms, say 15, 45, and 135, and we divide 135 by 45, so that's the Tn plus 1 divided by Tn, and then compare that with Tn divided by Tn minus 1, and we get the same value, the same ratio, then we can conclude that the sequence is geometric. So 135 over 45 equals 3. 45 over 15 also equals 3. So therefore, the sequence is geometric with the first term being 5, so a equals 5, and the common ratio is 3. Let's have a look at part B. 5, 10, 15, 20. Now, this we know is an arithmetic progression. So if we take any term and we just add 5 to it, we get the next term. So clearly this is not geometric, but let's prove the point. And we're going to use this rule here. This is the Tn plus 1 times Tn minus 1 is equal to Tn squared, and compare and check to see they are the same. So again, choose 3 consecutive terms. So for example, I'll choose 10, 15, and 20. 10 multiplied by 20 is 200, so that's the Tn plus 1 multiplied by Tn minus 1. And then let's square the term in the middle. So this 15, so if we square that, 15 squared is equal to 225. They're clearly not the same, so therefore the sequence is not geometric. So either definition is fine. Let's have a look at one more example. So if we have a look at part C. So we have pi cubed, pi to the power of 5, pi to the power of 7, and so on. Again, let's just choose any 3 consecutive terms. You can choose 4 consecutive terms if you like as well. So just for prudence, if you want to just make sure 100% or at least as much as possible that this is a GP, you can test as many terms as you like, but the minimum number of terms is 3. Again, I'm going to choose pi cubed, pi to the power of 5, pi to the power of 7. Pi to the power of 7 divided by pi to the power of 5 is pi squared. And pi to the power of 5 divided by pi cubed is, again, pi squared. So there's our common ratio. So therefore, the sequence is geometric with the first term a equals pi and the common ratio r equals pi squared. So just as another side note, if we have 3 terms, let's say a, b, c, and they form a geometric progression, then b squared is equal to ac. And we've seen that already with this test here. So imagine that's b squared, and that's a and c. Okay. So if a, b, and c form a GP, then b squared is equal to a times c. And if we take the square root of both sides, b is equal to plus or minus the square root of ac. This is actually known as the geometric mean. So just as a little side note there. Example 2. Write out the first few terms of the GP with a equals 4 and r equals 3 and determine the value of the 13th term. So we can use the non-recursive formula for the general term of a geometric progression. That is, the nth term, Tn, is equal to the first term a multiplied by r to the power of n minus 1, r being the common ratio. And we need n minus 1 common ratios because we start off with the first term, but to get to the second term, we just multiply by 1 lot of r. To get to the third term, we multiply by 2 lots of r, so r times r and so on, hence why it's n minus 1. So in this example, a is equal to 4, common ratio is equal to 3, so Tn, the nth term of this particular GP, is equal to 4 times r to the power of n minus 1, of course with n equals 1, 2, 3, and so on. So the first few terms of this GP, starting off with 4, multiply that by 3, we get 12. Multiply that by 3 again, we get 36. Multiply that by 3 again, we get 108, and so on. Now to get the 13th term, we can just apply the formula directly. So T13, so that's the 13th term, is equal to 4 times 3 to the power of 12. So it's n minus 1, 13 minus 1. And that equals 2,125,764. Example 3. Find a non-recursive formula for the GP given by the recursive formula Tn equals Tn minus 1 multiplied by negative 2, where T1 is equal to 3. Now firstly, let's write out the first few terms of the GP just so we can see a pattern. Now, T1 equals 3 refers to the first term, A. So starting off with 3, to get to the next term, we multiply by negative 2, so 3 times negative 2 equals -6. -6 multiplied by -2 is +12. +12 multiplied by -2 is -24. And -24 multiplied by -2 is +48. So notice that you get like an alternating pattern here, positive, negative, throughout this GP. And that's a hallmark of any GP that has a negative ratio, in fact. Next, let's find the common ratio. Now, we don't need to prove that this is a GP. In fact, we're told this in the question, so no need to spend sort of extra time on that. So all we need to do is just pick any two consecutive terms. So I've just chosen T3 and T2. So to find the common ratio, I just take T3 divided by T2. So there's T3 divided by T2, 12 over -6, and that gives us a common ratio of -2. So again, any two consecutive terms will be fine and will give you an R value of -2. Finally, we can find the non-recursive formula for Tn. And of course, Tn is given by the formula A times R to the power of n minus 1. And we've determined the first term and the common ratio. So A equals 3 and R equals -2. Therefore, Tn is equal to 3 times -2 to the power of n minus 1. Or if you want to simplify that further and just express it just in terms of n rather than a power of n minus 1, in fact, we could write it as Tn equals -3 over 2 multiplied by -2 all to the power of n. So either one of those two formulas will suffice. Example 4. Determine whether 320 and 720 are terms of the GP, 5, 10, 20, and so on. Now, to help us with this problem, we will use the formula for the nth term of a GP, that is Tn is equal to AR to the power of n minus 1, where A represents the first term and R represents the common ratio. Now, if Tn is a part of that GP or part of that sequence, then there will be a positive integer value of n such that AR to the power of n minus 1 will give us that Tn. So we're using this formula in reverse and just solving for n each time. And what we're looking for here is a value of n that is a positive integer that corresponds to the position of the particular value in that sequence. So it doesn't make sense to have a decimal value for n, since position or rank is a whole number. So firstly, let's test Tn equals 320. So we're going to solve this equation for n and see or check that n is in fact a positive integer. Hopefully it is. 5 times 2 to the power of n minus 1 is equal to 320. Dividing both sides by 5, we have 2 to the power of n minus 1 equals 64. And we can see by inspection that 64 can be expressed as a power of base 2. So 64 is equal to 2 to the power of 6. And just re-expressing this equation here as 2 to the power of n minus 1 equals 2 to the power of 6, and then equating the indices, we can see that n minus 1 equals 6, therefore n equals 7. That's a positive integer. In fact, that corresponds to the 7th term of the GP. So 320 is the 7th term of this particular GP. Let's have a look at 720. I'm going to test Tn equals 720 in the same way. So 5 times 2 to the power of n minus 1 is equal to 720. Dividing both sides by 5, we have 2 to the power of n minus 1 is equal to 144. Now at this point, without using logarithms, we can see by inspection that there's no integer power of n or integer power of base 2 that'll give us 144. In fact, the closest one will be 128, then it goes to 256 and so on. However, just for completeness, let's use logarithms here to find the value of n and then show that that value of n is not an integer, nor is it a positive integer for that matter. So taking the natural log of both sides, so ln of 2 to the power of n minus 1 is equal to ln of 144. Applying log law number 3, so we can take the n minus 1 out to the front. So this becomes n minus 1 in brackets multiplied by ln of 2 is equal to ln of 144. Dividing both sides by ln of 2 and then adding 1 to both sides, we have n equals 8.1699 and so on, which is not an integer. Not a positive integer, but it's not an integer altogether. So therefore, 720 is not part of the geometric progression. Example 5. The third term of a geometric progression is 12 and the 7th term is 972. write out the first few terms of the geometric progression. Now we'll use the formula for the nth term of a GP, Tn equals a times r to the power of n minus 1. And we have two known values or two known terms in the sequence. So we have the third term, T3 is equal to 12, and we have T7, the seventh term, is equal to 972. So the strategy here is to form two equations using this formula and then solve it simultaneously for A and R. So using T3 equals 12, 12 is equal to a r to the power of n minus 1, so n minus 1 in this case will equal 2, and our second equation will be 972 is equal to a r to the power of 6, so 7 minus 1 gives us 6 there, and then dividing 2 by 1, so equation number 2 by equation number 1, we can then solve for r, then we can solve for a. So 972 divided by 12 is equal to ar to the power of 6 divided by ar squared. Now the a's cancel. We have r to the power of 6 divided by r squared is equal to 972 over 12. 81 is equal to r to the power of 4. Now because the power of r, the index of r is an even number, we're going to have a positive and a negative value for r, or they're the two possibilities. So r is equal to plus or minus the 4th root of 81. That's the square root of the square root of 81. And we need to consider both cases. So hence r equals negative 3 or positive 3. Now either one of those two values for r, if you use say equation number 1 to determine the value of a, we have 12 equals a multiplied by plus or minus 3. It doesn't really matter. You're going to square it. It's going to become either 0 or positive anyway. And we end up with a equals 1 1/3. So to write out the first few terms of this GP, we have a is equal to 1 1/3, and the common ratio r is either positive 3 or negative 3. And we need to consider both cases because we're not given any other information in the question. We might be told, or could be told, that r is positive or r is negative. In that case, just state the particular sequence based on that value of r. But since we're not told, we need to state both possibilities as they are both valid solutions. So case 1, r is equal to negative 3. The GP is 1 1/3, negative 4. So just multiplying everything by negative 3, or the previous term by negative 3 to get the next term along. So 1 1/3, negative 4, positive 12, negative 36, positive 108, and so on. So you can see that alternating pattern there with the plus or minus terms. Now case 2, r is equal to positive 3. And since we're starting with a positive first term, or positive a, all the terms will be positive. So it's very much like case 1, just all terms positive. So the GP is 1 1/3, 4, 12, 36, 108, and so on. Example 1a. Find the value of m given 5, m, 20 forms an arithmetic progression. Now since these three terms form an AP, they're consecutive terms, there is a common difference between these three terms. In other words, m minus 5 will equal 20 minus m. So we can form an equation to that effect and then solve for m. So m minus 5 is equal to 20 minus m. Adding m to both sides and adding 5 to both sides, we have 2m equals 25, and then dividing both sides by 2, we have m is equal to 12.5. Now there is an alternative solution, which is very similar to the first method, but it uses the fact that m is the average of 5 and 20, and it uses that fact explicitly. So Tn is equal to Tn minus 1 plus Tn plus 1, so they refer to the terms on either side of m, and then divide that by 2. M is equal to 5 plus 20 over 2, and therefore m is equal to 12.5. So the AP is 5, 12.5, and 20. Now let's have a look at an example involving a geometric progression. So part B, example 1b, find the value of b given 5, b, 20 forms a geometric progression. Now since these three terms form a GP, there is a common ratio between these three terms. So in other words, b divided by 5 will equal 20 divided by b. So we can form an equation again to that effect. So b over 5 equals 20 over b. With cross multiplication, we get b squared is equal to 100. We take the square root of both sides. we get b is equal to plus or minus 10. So there's two values for b. So there's two GPs. So one case is b is negative 10. We have 5, negative 10, 20. Or if b is positive 10, 5, 10, and 20. Example 2. The third term of an arithmetic progression is 16 and the 12th term is 79. Find the 50th term. Let's write down what we know. We know that T3 is equal to 16. So when n equals 3, T3 is 16. We know that when n equals 12, T12 is equal to 79. So we want the value of T50, in other words, the value of the term when n equals 50. So we need to use the formula for the nth term of an AP. So Tn is equal to a plus n minus 1d. We're going to form two equations using that formula and then solve that simultaneously to find the values of a, the first term, and the common difference d. So using T3 equals 16 and forming our first equation, we have 16, so T3, 16 is equal to a plus n minus 1d. Now n is 3, so 3 minus 1 is 2. So the formula is 16 equals a plus 2d. Now using the fact that T12 is equal to 79, we can form another equation. So 79 is equal to a plus 11d. So again, n minus 1, 12 minus 1 is 11. So we have this second equation here. Now we need to solve simultaneously for a and d. And we can use the elimination method because we can easily eliminate a by subtraction. So equation 2 minus equation 1, we have 79 minus 16 is 63. A minus a is 0, of course, and 11d minus 2d is 9d. And dividing both sides by 9, we get d is equal to 7, so that's the common difference. Now using either of the two equations in the simultaneous equation, either equation 1 or 2, whichever is the more convenient, I'm just going to use equation 1, substituting in d equals 7 into equation 1, and then just rearranging the formula, we can determine the value of a. So from 1, 16 is equal to a plus 2 times 7. 16 is equal to a plus 14, hence a is equal to 2, so that's the first term of this AP. So to work out T50, we just use the nth term for an AP formula. So T50 is equal to 2 plus n minus 1, so 50 minus 1 is 49, multiplied by the common difference 7, and we get T50 is equal to 345. So therefore the 50th term is 345. Example 3. The fourth term of a geometric progression is negative 128 and the seventh term is 8,192. Find the first term, the common ratio, and the 100th term, leaving your answer in simplest index form. Let's start by writing down what we know. We know that T4 is equal to negative 128. We know that T7 is equal to 8,192. We need to find T100. But to find T100, the 100th term, we need to find A and R. So the first term and the common ratio. Now recall that the formula for the nth term of a geometric progression is Tn is equal to AR to the power of n minus 1. So we can use that to then form two equations which we can then solve simultaneously. So we know that T4 is equal to negative 128. So the equation we can form is negative 128 is equal to A multiplied by R to the power of n minus 1. Now n is 4 in this case, so 4 minus 1 is 3. So equation 1 is negative 128 equals AR to the power of 3. The second equation we can form is based around T7. 8,192 is equal to AR to the power of 6, of course, because it's 7 minus 1, n minus 1 equals 6. Now we can solve this simultaneously. We do that by taking equation 2 and dividing it by equation 1. So 8,192 divided by negative 128 is negative 64. And AR to the power of 6 divided by AR to the power of 3 is equal to R cubed. And then taking the cube root, of course, of both sides. So we have R is equal to the cube root of negative 64. And therefore R is equal to negative 4. So there's only one common ratio here, not two cases like in previous examples where you could have a positive R and a negative R. In this case, it's only a negative r. So we can use either equation 1 or 2 now to find the value of a. I've just chosen equation 1. Negative 128 equals a multiplied by negative 4 cubed. So we can use our value of r now that we found, substitute it in here for r, and then solve for a. And we end up with a equals 2. Now we can find the 100th term. So let's again write down what we've just discovered. So we know the first term is 2. We know the common ratio is negative 4. We need to find T100. Using the formula for the nth term of a geometric progression, Tn is equal to a multiplied by r to the power of n minus 1. So T100 is equal to 2 multiplied by negative 4 to the power of 99. Now because this is an odd power, the negative sign can come out to the front. So that equals negative 2 multiplied by 2 squared. So I've got sort of two things here at once. I've also written the 4 as 2 squared because I can combine these two bases together. So using the power to a power rule, 2 squared to the power of 99 is 2 to the power of 198, and we're going to multiply that by negative 2. So combining all those together, so we have a common base here of 2. This equals negative 2 to the power of 199, and this corresponds to the 100th term of this geometric progression. Example 4. Find the first term greater than 1 million in the GP 3, 3 root 2, 6, and so on. So we're going to solve for n, given that Tn is greater than 1 million in the formula Tn equals AR to the power of n minus 1. So this is the formula for the nth term of a geometric progression, but we want to find the smallest n such that Tn is greater than 1 million. Now a is equal to 3, and the common ratio is square root of 2. So again, we're told this is a GP, so there's no need to prove this. But 3 root 2 divided by 3 is just root 2, so that's the common ratio. So the inequality becomes 3 outside of square root of 2 to the power of n minus 1 is greater than 1 million. And dividing both sides by 3, we have the square root of 2 to the power of n minus 1 is greater than 333,333 and a third. So now we take logs of both sides, and you can use any base, but I'm just going to use log base 10. I know in a previous example I used the natural log, so ln, but you can use log base 10. So log base 10 of square root of 2 to the power of n minus 1 is greater than log base 10 of 333,333 and a third. And we can use one of the log laws here, so log law number 3, to take out the n minus 1 and bring that out to the front. So n minus 1 multiplied by log base 10 of square root of 2 is greater than log base 10 of 333,333 and a third. And then dividing both sides by log base 10 of square root of 2, we can make n the subject of the inequality, and we end up with n greater than 37.69 ... So the next integer greater than this value is n equals 38. So that corresponds to the position of the term that's the first term that's greater than 1 million. So that's going to be the 38th term. So we need to determine what that term is. So T38 is equal to 3 multiplied by the square root of 2 to the power of 37. That's n minus 1. And then just evaluating that, and I'm just going to round it to one decimal place, or we can keep it in exact form. It doesn't really matter. It just depends what the question's asking, of course. And we end up with 1,112,182.8, and that's correct to one decimal place. Example 1. Given the arithmetic progression 5, 15, 25, and so on, A, find S6. Now S6 represents the sum of the first 6 terms of this arithmetic progression. So the sum of the first 6 terms is 5 plus 15 plus 25 plus 35 plus 45 plus 55, and that equals 180. Part B, show that S6 minus S5 is equal to T6. So that's the sum of the first 6 terms minus the sum of the first 5 terms of this arithmetic progression. And we need to show that it equals the 6th term of this arithmetic progression. So S5 is equal to 5 plus 15 plus 25 plus 35 plus 45, and that equals 125. Now S6 we've worked out from part A, which is 180. So S6 minus S5 is equal to 180 minus 125, which equals 55, which equals T6 as required. Now it is worth noting that Tn, or the nth term of an AP, is equal to the sum of the first n terms minus the sum of the first n minus 1 terms. And T1 is equal to S1. That is, the sum of, well, the first term, or the only term, which is just the first term, is also equal to T1, which represents the first term as well. And this is a useful starting point when dealing with problems involving sums of arithmetic progressions. Example 2. State the first 5 terms of the sequence of partial sums, S1, S2, S3, S4, S5, given the arithmetic progression 2, 5, 8, and so on. S1 represents the sum of one term of the AP. S2 represents the sum of the first 2 terms. S3 represents the sum of the first 3 terms, and so on. The AP itself, 2, 5, 8, has first term of 2, common difference of 3. Now S1 is just equal to T1. So therefore S1 is equal to 2. It's just the sum of one term. S2 can be found either by S1 plus T2 or just T1 plus T2. So first sum of the first 2 terms. So therefore S2 is equal to 7. Now S3, so the sum of the first 3 terms, can be found by taking S2, which has already been determined, and then adding on the third term. So 7 plus 8 equals 15. So therefore S3 equals 15. Now the next term along in the AP is 11. S4 is equal to S3 plus T4, which is 11. And S3 is the sum of the first 3 terms, so that's been determined already, that's 15, plus 11. Therefore S4 is equal to 26. Now the fifth term along, adding 3 to 11, is 14. So S5 is equal to S4, which has already been determined as 26, adding on 14, and therefore S5 is equal to 40. So therefore, the sequence of partial sums of the AP is 2, 7, 15, 26, and 40. So notice also that this particular sequence is not an arithmetic progression. After all, the common difference, well, there is no common difference, and the terms seem to go up by bigger and bigger amounts each time. So just as a bit of a recap, this is the sum of one term, sum of 2 terms, sum of 3 terms, sum of 4 terms. So these terms are in fact cumulative. Example 3. Write the first 5 terms of the arithmetic progression given S8 equals 92, S9 equals 117, and S10 equals 145. Now S8, S9, and S10 represent partial sums of this arithmetic progression. S8 represents the sum of the first 8 terms, S9 represents the sum of the first 9 terms, and S10 represents the sum of the first 10 terms. Now we can use this rule here, Sn equals Sn minus 1 plus Tn, and we've seen this in a previous example. So the sum of the first n terms can be found by taking the sum of the first n minus 1 terms and then adding on to that Tn, the nth term. Rearranging this formula, we have Tn, so the particular term in this AP, or the nth term, can be found by taking the sum of the first n terms and then subtracting from that the sum of the first n minus 1 terms. So let's find T10, since we have S10 and S9. So T10 is equal to S10 minus S9. T10 is equal to 145 minus 117. So we have T10 is equal to 28. Likewise, and using the same method, we can find T9. T9 is equal to S9 minus S8. T9 is equal to 117 minus 92. Therefore, T9 is equal to 25. So we know that these two terms form an AP. And we also know that this is the 10th term, this is the 9th term. So let's find the common difference. So you can subtract T9 from T10. So D is equal to 28 minus 25. So therefore D equals 3. A common difference of 3 there. Now to find A, the first term. So I'm going to use T10 here. T10 equals 28. Well, no, that's the 10th term. And that's equal to A plus N minus 1D. So 28 is equal to A plus 27. And therefore, A equals 1. So therefore, the first 5 terms of this AP is 1, 4, 7, 10, and 13. Example 4. Given Sn equals n squared, show that this forms an arithmetic progression consisting of the sequence of odd numbers 1, 3, 5, and so on. Now we can apply the rule that Tn is equal to Sn minus 1. That is, the nth term of this arithmetic progression is found by taking the sum of the first n terms and subtracting from that the sum of the first n minus 1 terms. Now in this case, Sn is equal to n squared, and S of n minus 1 is equal to n minus 1 all squared. So expanding this perfect square and then expanding the brackets a second time to take into account this negative, we get Tn is equal to n squared minus n squared plus 2n minus 1. The n squareds will cancel. So we have Tn is equal to 2n minus 1, where n is equal to 1, 2, 3, and so on. Now we can express Tn equals 2n minus 1 in A plus n minus 1D form. And we can see that this represents the AP 1, 3, 5, 7, 9, and so on. In fact, this form here, I've just included that just so you can see that it can be expressed using the A plus n minus 1D form. However, we don't need to express it in this way. We can still use just 2n minus 1. So if you substitute n equals 1 into this Tn formula here, the nth term formula here, 2 times 1 is 2 minus 1 is 1. Substitute n equals 2. 2 times 2 is 4, 4 minus 1 is 3, and so on. Example 5. Evaluate the following sums. Part A, the sum from n equals 4 to 7 of 3n plus 1. And B, the sum from n equals 2 to 6 of negative 2 all to the power of n. Let's have a look at part A. So when n equals 4, 3 times 4 plus 1 is 13. When n equals 5, 3 times 5 plus 1 is 16. When n equals 6, 3 times 6 plus 1 is 19. And when n equals 7, 3 times 7 plus 1 is 22. The sigma notation just means add them up. It's just the sum. So 13 plus 16 plus 19 plus 22 equals 70. Part B, the sum from n equals 2 to 6 of negative 2 all to the power of n. So we'll just form the sequence and just add them up. So negative 2 all squared, so that's when n equals 2. So negative 2 all to the power of 2 plus negative 2 all to the power of 3 plus negative 2 all to the power of 4 plus negative 2 all to the power of 5 plus negative 2 all to the power of 6. So that's what it means from n equals 2 to 6. So 2, 3, 4, 5, and 6. And so all the even powers, of course, will result in positive values, and all the odd powers will result in negative values. So this evaluates to 4 minus 8 plus 16 minus 32 plus 64, which equals 44. Example 1. Find the sum of the first 5 terms of the arithmetic progression, 7, 10, 13, and so on. Now we're only talking about 5 terms, so it's easy enough to just list the 5 terms and add them up. So 7 plus 10 plus 13 plus 16 plus 19 equals 65. The problem's not as easy if it was, say, to find the sum of the first 50 terms or the first 500 terms or 5,000 terms. There is an alternative method, and that is to find the mean of the partial sequence. In this case, we only want the first 5 terms of this sequence, and then multiply that mean by the number of terms of that partial sequence. So in this example, We can find the mean by taking the average of the first and last terms of this partial sequence. So the average of 7 and 19. So 7 plus 19 divided by 2 equals 13. And since there's 5 terms in this partial sequence, to find the partial sum, we then take the mean, multiply it by 5, since there's 5 terms, and that gives 65. Example 2. Find the sum of the first 500 terms of the arithmetic progression, 7, 10, 13, and so on. Now this is similar to example 1. The only change is that instead of the first 5 terms, we're looking at the sum of the first 500 terms. And we're going to use the alternative method. That is, we find the average or the mean of the first and last terms of the partial sequence and then multiply it by the number of terms of the partial sequence to then find the sum of that sequence. So the first term of the sequence is 7. Now the last term of the partial sequence, that's the 500th term, T500, is equal to 7 plus 499 multiplied by 3, so that's the a plus n minus 1d, and that equals 1504. So the partial sum of the arithmetic progression is equal to 7 plus 1504 divided by 2, so that's the average of the first and last terms, multiplied by 500, because that's the number of terms that we want to add together, first 500. And that equals 377,750. Example 3. Find the sum of the arithmetic progression 3, 7, 11, all the way up to 4,815. Now in this example, we know the first term, we know the last term, we know the common difference, which is 4, but we don't know the number of terms. So the first thing we need to determine is how many terms are there in this partial sequence. Once we have that, we can then determine the partial sum of this arithmetic progression. So let's determine n first. So Tn is equal to 4,815. So I go straight to the last term and determine what value of n would give me the last term. So 4,815 is equal to 3 plus n minus 1 times 4. And we're going to solve for n. So this is the formula for the general term or the nth term of an arithmetic progression. Subtracting 3 from both sides, 4,812 is equal to n minus 1 in brackets multiplied by 4. Dividing both sides by 4, we have 1,203 is equal to n minus 1. Adding 1 to both sides, we have n is equal to 1,204. So there are 1,204 terms in this arithmetic progression that we want to add together. So the partial sum of the first 1,204 terms of this arithmetic progression is found by taking the average of the first and last terms and then multiplying it by the number of terms. So 3 plus 4,815 divided by 2 multiplied by 1,204, and that equals 2,900,436. Example 4. Find the sum of the first n terms of the arithmetic progression a plus d, a plus 2d, and so on. Now the first term of this AP is a, and the last term is a plus n minus 1d. There are n terms that we're going to add together in this arithmetic progression. So let's use the same formula that we used in the previous examples. That is, the partial sum is found by taking the average of the first and last terms and then multiply it by the number of terms that we're going to add together. So the partial sum is equal to a plus n minus 1d, so first and last terms, the average of those two. Multiply that by n, and we get n over 2 outside of a plus n minus 1d. So that n over 2 just comes from this n and this 2 here. So I'll just put them out at the front. And combining the two a's together, we get partial sum equals n over 2 outside of 2a plus n minus 1d in brackets. And this is the alternative formula to the sum equals the average of the first and last terms multiplied by the number of terms in the sum. Example 5. Given the arithmetic series 100 plus 94 plus 88 and so on, find S41. Now S41 represents the sum of the first 41 terms of this series. And we're going to use the alternative formula, Sn equals n over 2 outside of 2a plus n minus 1d. And the advantage of this formula is that you don't need to find the last term explicitly so that you can average it with the first term and then multiply it by the number of terms. It's built into this formula. Now, a equals 100, we know that. D is equal to -6, that's a common difference, and we're going to sum the first 41 terms. So substituting these three values into the formula, we have S41 is equal to 41 over 2 outside of 2 times 100 plus 40 times -6, that's the n minus 1 there, and that equals -820. Example 6. Given the arithmetic series 40 plus 37 plus 34 and so on, find the least value of n for which the partial sum is negative. Now the strategy here is we're going to solve the inequality for n over 2 outside of 2a plus n minus 1d less than 0. The left hand side represents the sum of the first n terms of this arithmetic series. So we want to find the smallest value of n such that the sum is negative. Now we know that a equals 40, it's the first term of this series, and the common difference is -3. So substituting these two values into the left-hand side, we have n over 2 outside of 2 times 40 plus n minus 1 times -3 is less than 0. We can multiply both sides by 2 and we can multiply the 2 and the 40 together and just clean it up a little bit. We get n outside of 80 minus 3 outside of n minus 1 in brackets less than 0. Now expanding the inner bracket there, we have n outside of 83 minus 3n less than 0. And if we divide everything by 3, we have n outside of 83 over 3 minus n less than 0. So therefore, n has to be greater than 83 over 3 or greater than 27 and 2/3. Hence, the first integer that's greater than 27 and 2/3 is 28. So therefore, S28 is the first sum that is negative. Example 1. Find the sum of the first 5 terms of the geometric series, 6 plus 12 plus 24 and so on. Now we're only talking about 5 terms, so it's easy enough to list the 5 terms and add them up explicitly. So the sum of the first 5 terms, so the partial sum, is equal to 6 plus 12 plus 24 plus 48 plus 96, and that equals 186. But what if the question asks for, say, the sum of the first 50 or the first 500 terms of the geometric series? So I've just came up with these numbers arbitrarily, a number big enough that it's not practical to list the terms explicitly. So like the sum of an arithmetic series, which we've seen before, there is a formula that we can use to add up any number of terms of an arithmetic series. Can we derive a formula for Sn for a geometric series? So following sort of in a similar pattern to an AP, can we do the same for a GP? Come up with a formula that, regardless of how many terms we're adding up, can we just apply a formula and we are done? And of course we can. So let's derive the formula for the sum of the first n terms of a geometric series. So let Sn, so the sum of the first n terms, the partial sum of the first n terms of a geometric series, be a plus ar squared plus ... ar to the power of n minus 1. So first term, second term, third term, and so on, right up to the last term. And we're just going to add them up explicitly, but we're expressing the terms in general terms. So we don't know the value for a and r. All we know is that they're there, and it forms a geometric series. And let's call that equation number 1. Next, we're going to multiply both sides of equation number 1 by the common ratio r. Now that does not change the integrity of the equation. As long as what you do to one side, you do to the other, and r is not equal to 0 for that matter as well. It is a geometric progression or a geometric series, so it follows the rules of a geometric series or progression. Now that gives us equation number 2. So r multiplied by Sn is equal to ar, so a times r is ar, so that's our first term now, plus ar squared plus ar cubed plus ... plus ar to the power of n. So ar to the power of n minus 1 multiplied by r gives us the last term here, ar to the power of n. We're going to call that equation number 2. Now, if we take equation number 1 and subtract from that equation number 2, we're going to get a lot of cancellation. So the ar squared from equation 1 will cancel with the ar squared from equation number 2 and so on. So what we end up with is Sn minus r times Sn is equal to a plus ar squared plus ... plus ar to the power of n minus 1 minus ar plus ar squared plus ar cubed plus ... plus ar to the power of n. So that's the right-hand side of equation 1, and that's the right-hand side of equation number 2. Now, if you expand the brackets, of course, you're going to get some cancellation. In this bracket here, you have the first term a, but there's no a in the second bracket. So this a here is retained. In the second bracket here, we have an AR to the power of n, but there's no AR to the power of n in the first bracket. So this term is retained, but all other terms will cancel. So if we factorize the left-hand side here, so taking Sn out as a common factor, we have Sn outside of 1 minus r is equal to a minus AR to the power of n. And if we factorize a from the right-hand side of this equation, we have Sn outside of 1 minus r is equal to a outside of 1 minus r to the power of n. Now, dividing both sides of this equation here by 1 minus r, we have the sum of the first n terms of the geometric series is equal to a outside of 1 minus r to the power of n in brackets divided by 1 minus r. And we can switch the 1 minus r around and the 1 minus r to the power of n around. So if you multiply top and bottom by -1, we also have an alternative formula, which is a outside of r to the power of n minus 1 in brackets over r minus 1. And of course, r cannot equal 1. Example 2. Find the sum of the first 20 terms of the following geometric series. Part A, 2 plus 4 plus 8 plus ... Now the first term is 2, common ratio is 2, and n equals 20. So the sum of the first 20 terms of this geometric series can be found by applying the formula a outside of 1 minus r to the power of n all over 1 minus r. So s of 20 equals 2 outside of 1 minus 2 to the power of 20 all over 1 minus 2, and that equals 2,097,150. Let's have a look at part B. 20 plus 10 plus 5 plus ... Now with this geometric series, a equals 20, common ratio is half, and n equals 20. So S20 is equal to 20 outside of 1 minus half to the power of 20 all over 1 minus half, and that equals 40 outside of 1 minus 1 over 2 to the power of 20, and that's roughly equal to 39.99996,185. And that's because 1 over 2 to the power of 20 is a very, very small number. In other words, it's a number very close to 0. So we're going to get a value that's pretty close to 40 in this case. Let's have a look at one more example. So part C, this geometric series, -3 plus 6 minus 12 plus ... So the terms are alternating in sign. The first term is -3. The common ratio is -2 and n equals 20. So the sum of the first 20 terms of this geometric series is equal to -3 outside of 1 minus -2 in brackets to the power of 20. So just be mindful here of using the brackets correctly, all over 1 minus -2. And that equals 1,048,575. Example 3. Find the geometric series given the sum of the first 5 terms is equal to 242, the sum of the first 6 terms is equal to 728, and the sum of the first 7 terms is equal to 2,186. Now we're going to use the fact that the nth term is found by taking the sum of the first n terms and subtract from that the sum of the first n minus 1 terms. So we can find the 6th term using this rule, and the 6th term is equal to the sum of the first 6 terms minus the sum of the first 5 terms. So T6 is equal to 728 minus 242, and that equals 486. Using the same idea, we can find the 7th term. So T7 is equal to S7 minus S6. T7 is equal to 2,186 minus 728, and that equals 1,458. Now the common ratio is found by taking a term and dividing it by the previous term. So Tn over Tn minus 1 is equal to R. Now we have T7 and T6, and we know that this is a geometric series or geometric progression. So the common ratio can be found by dividing T7 by T6. So R is equal to 1,458 divided by 486, and we get R equals 3. Now we need to find the first term, A. We know that T6 is equal to 486 and that R equals 3. We could also use T7, but I thought T6 is probably as convenient, if not more so, because it's a smaller number. So to find A, we're going to equate 486 with AR to the power of 5. So the sixth term is equal to AR to the power of n minus 1. So 6 minus 1 is 5. We know R, so we're going to substitute 3 for R here. So 486 is equal to A multiplied by 3 to the power of 5. Let's make A the subject of the formula. So A is equal to 486 divided by 3 to the power of 5, and that equals 2. So the geometric series is 2 plus 6 plus 18 plus 54, and so on. Example 4. Determine the minimum number of terms of the geometric progression 2 plus 8 plus 32 plus ... that must be added for the sum to exceed 10 to the power of 15. Let's write down what we know. We know the first term is 2 and the common ratio is 4. We don't know n, that's what we're trying to determine. So we're going to solve the inequality. Sn is greater than 10 to the power of 15 for n. So the sum of the first n terms is given by the formula 2 outside of 1 minus 4 to the power of n over 1 minus 4. So that's A outside of 1 minus r to the power of n over 1 minus r. And we're going to solve the inequality. Left-hand side is greater than 10 to the power of 15. So let's rearrange the inequality. So multiplying both sides by negative 3. So that's 1 minus 4 is negative 3. We need to reverse the inequality sign. So we get 2 outside of 1 minus 4 to the power of n less than negative 3 multiplied by 10 to the power of 15. Dividing both sides by 2, we have 1 minus 4 to the power of n less than negative 3 over 2 multiplied by 10 to the power of 15. If we multiply both sides by negative 1, so that instead of having negative 4 to the power of n, we just have 4 to the power of n. It does make life a little bit easier. We get 4 to the power of n minus 1 greater than, so we reverse the inequality symbol yet again, greater than 3 over 2 multiplied by 10 to the power of 15. Finally, we add 1 to both sides. So we have 4 to the power of n greater than 3 over 2 multiplied by 10 to the power of 15 plus 1. Now, if we take the log of both sides, and we're going to use log base 10 here, and apply the logarithm law where the power comes out to the front, the n comes out to the front, we have n multiplied by log base 10 of 4 is greater than log base 10 of 3 over 2 multiplied by 10 to the power of 15 plus 1. So dividing both sides by log base 10 of 4, we have n greater than log base 10 of 3 over 2 multiplied by 10 to the power of 15 plus 1 divided by log base 10 of 4. So if we evaluate the right hand side, we get n is greater than 25.2. So the next integer along is n equals 26. So we need to sum the first 26 terms of this geometric progression to get a sum exceeding 10 to the power of 15. Example 1. An empty 20-litre bucket is being filled with water. At first, 10 litres of water is poured into the bucket, then another 5 litres, and then another 2.5 litres, and then another 1.25 litres, and so on. Will the bucket ever fill up to capacity? Now, this situation here can be modelled using a geometric series. Let Sn represent the capacity of water in the bucket after the nth fill. So the amount of water in the bucket after the first fill is S1, and that's 10 litres. The amount of water in the bucket after the second fill, so that's 10 litres plus half of 10, that's 5. In total, that's 15 litres of water now in the bucket. After the third fill, so 10 litres plus 5 litres plus 2.5 litres is equal to 17.5 litres. So we can see that the amount of water in the bucket's increasing, but the question is, will it ever reach 20 litres, so that's the capacity of the bucket, or might it even exceed 20 litres and water will pour out? Let's find out. So this scenario can be modelled using the sum of a geometric series using the formula Sn equals A outside of 1 minus r to the power of n over 1 minus r. Now the first term is 10, so that represents the first fill, T1, so A equals 10, and the common ratio is half, since the next fill is half of the fill before it. And n is equal to infinity. We're going to keep on going, keep on filling this bucket half each time, or half of the previous amount each time, forever and ever. Now let's see what happens. So the capacity of water in the bucket after infinity fills is S infinity, or the sum to infinity. So let's see what happens when we let n, this index here, equal infinity. Now S infinity is equal to 10 outside of 1 minus half to the power of infinity over 1 minus half. Now a little side note here, that if the common ratio is between -1 and 1 and not equal, of course, to -1 or 1, but must be strictly in between -1 and 1, then r to the power of infinity is equal to 0. So S infinity is equal to 10 outside of 1 minus 0 over half. So therefore, S infinity is equal to 20 litres. So this means that the bucket will eventually fill. Now, that's in theory, and practically speaking, well, you need to keep filling this bucket infinite times, but we know that practically that's very difficult, of course. But in theory, the bucket will eventually fill up. Example 2. Find the limiting sum of the geometric series 18 plus 6 plus 2 and so on. Now since the absolute value of r is less than 1, that is, the common ratio is between -1 and 1, then the absolute value of r to the power of infinity is equal to 0. Using that property, we can come up with a formula for the limiting sum of a geometric series. S of infinity is equal to a outside of 1 minus the absolute value of r to the power of infinity over 1 minus r. But the absolute value of r to the power of infinity is equal to 0. So that kind of wipes out this term here, becomes 0, and then we're left with S of infinity, or the infinite sum, is equal to a over 1 minus r, where a represents the first term of the geometric series. Now in this example, a is equal to 18 and r is equal to 1/3. So S of infinity is equal to 18 over 1 minus 1/3, and that evaluates to S of infinity equals 27. Now, as a side note, this is known as a converging series as opposed to a diverging series, in that Sn approaches c, or some constant, or some definite value, as n approaches infinity. Example 3. For what values of x does the series 1 plus x minus 2 plus x minus 2 all squared plus ... converge? Now the series converges if and only if the absolute value of r is less than 1. That is, the common ratio needs to be strictly between -1 and 1, where r cannot equal 0. So let's find the common ratio. Just take any two consecutive terms and divide one by the other. So the latter term divided by the term previous. So the common ratio is equal to x minus 2 all squared divided by x minus 2, or you could do x minus 2 divided by 1, either way. The common ratio is x minus 2. Now we want x minus 2 to be between -1 and 1. So adding 2 to all three parts of this inequality, we get -1 plus 2 is less than x minus 2 plus 2 is less than 1 plus 2, which gives us x between 1 and 3. So the series converges when x is between 1 and 3, with the sum to infinity equal to 1 over x minus 2. Example 4. Find the ratio of a geometric progression whose first term is 15 and whose limiting sum is 100. We're going to apply the formula. The limiting sum is equal to a over 1 minus r, where a is the first term and r is the common ratio. Now we know the limiting sum and we know the first term, so we need to solve for r. So substituting in 100 for the limiting sum and 15 for a, we have 100 is equal to 15 over 1 minus r. Swapping the 100 and the 1 minus r around, we have 1 minus r is equal to 15 over 100, and then making r the subject of the formula, we have r is equal to 1 minus 15 over 100, or 17 over 20. Example 1. By expressing 0.1 recurring as a geometric series, show that 0.1 recurring equals 1 over 9. Now 0.1 recurring is equal to 0.1 plus 0.01 plus 0.001 plus ... The pattern continues forever, so there's an infinite number of terms. Using fractions, this can be written as 1 over 10 plus 1 over 100 plus 1 over 1,000 plus 1 over 10,000 and so on. Now this is a converging geometric series with the first term a equals 1 over 10 and the common ratio r equals 1 over 10. So substituting 1 over 10 for a and r in the limiting sum formula, we have the limiting sum equals a over 1 minus r, which equals 1 over 10 all over 1 minus 1 over 10, which equals 1 over 10 divided by 9 over 10, which equals 1 over 9 as required. Example 2. By expressing 2.613, where the 1 and the 3 recur as a geometric series, show that it can be written as the mixed numeral 2 and 607 over 990. Now 2.613, where the 1 and the 3 recur, can be written as 2.6 plus 0.013 plus 0.00013 and so on. And this pattern continues forever. So there's an infinite number of terms. Now notice that the geometric progression starts from 0.013, not from the 2.6. That's a separate term altogether. It's got nothing to do with the geometric progression. Now expressing the right-hand side in fraction form, 2.6 is equal to 13 over 5. 0.013 can be written as 13 over 100, and 0.00013 can be written as 13 over 100,000, and so on. Now this is a converging geometric progression, where the first term is 13 over 1,000, and the common ratio is 1 over 100. And because it's a converging series, we can apply the limiting sum of a geometric progression formula. That's the s, infinity, is equal to a over 1 minus r. So it's equal to 13 over 5. Now that's a separate term, it's got nothing to do with the GP, plus a over 1 minus r. So the a is 13 over 1,000 over 1 minus 1 over 100. That's the 1 minus r. And that equals 13 over 5 plus 13 over 990. Just adding those two fractions in your calculator, we get 2 and 607 over 990 as required.